Good afternoon. I'm MD Shoel Rana and I'm pursuing my PhD in computer science at the University of Southern Mississippi. Today we are going to learn one of the well-known sorting algorithm, Quicksort. So before going to learn the Quicksort, first we would like to learn the basics for a sorting algorithm. So what is the technique behind sorting algorithm? A technique that is used for rearranging a set of unordered items into a finite sequence or order, like alphabetical, lowest to highest value, or longest to shortest distance, is called sorting algorithm. In sorting algorithms, unordered items are given as input and delivered ordered list as output by performing precise actions on those items, right? The most used application of sorting algorithms includes forming or displaying items by their price on different e-commerce websites. For example, Amazon, eBay, Walmart, etc. Even we can say another example like defining the order of sites by alphanumeric order on a search engine results page. So the importance of sorting is to search data can be improved while data is kept in a sorted way. And we know that there are two types of sorting. One is internal sorting, where the number of items is small enough to fit into the main memory. And the second one is external sorting, where the number of items is so large that some of them reside on external storage during the sort. And we know that a lot of sorting algorithms have already been developed, and these algorithms have enhanced the performances in the factors, including time and space complexity, stability, correctness, finiteness, and effectiveness. So, what are the contents we are going to cover today? We are going to cover what is quicksort. Then we will learn the basics of quicksort. After then, we will perform a complexity analysis on quicksort. That means time complexity, space complexity. And we will also prove the correctness of this correct quicksort. So now, the question is, what is quicksort? Quicksort is one of the efficient and most commonly used algorithms. Most of the languages used quicksort in their inbuilt sort methods implementations. The name comes from the fact that it sorts data faster than any commonly available sorting algorithms like merge sort. It also follows the divide and conquer principle like merge sort. And quicksort in particular is an interesting one. Nevertheless, it takes enough time to get your head around it. Quicksort breaks down the problem of sorting the complete arrays into smaller sub-problems or smaller problems by breaking down the array into smaller sub-arrays. This technique of splitting the bigger problems into smaller problems is called divide and conquer approach. So what we learn from here? We learn that the quicksort always follow divide and conquer strategy. So since the divide and conquer strategy followed by the quicksort, so what is actually the divide and conquer rules, right? So in divide and conquer rule, there are three steps. One is divide, another one is conquer, and third one is combine. So what divide actually does, right? Divide actually make a partitions the array into two sub arrays, right? For example, we have an array A. The index starts from left to right. Left means the leftmost, the zero index, and right means the rightmost. So, for example, the divide actually makes a dividation or makes a partitions into two sub arrays. The first array we can treat this first array as A1 and the second array should be A2. So we can actually divide makes the partition for a certain position. For example, in case the P is the index where it actually makes the partition. So Based on this divide and conquer theory, we will see that each element, the left side of this P index, must be smaller than the P index value. And the elements that are next to the P index element, that must be greater than the P index values, where the P index actually computed as a part of the partitioning procedure. Now the steps conquer. Conquer actually sorts the two sub-arrays by recursive calls, right? And the final step is combine. But in case of quicksort, the sub-arrays are sorted in place. That's why no work is needed to combine them, right? So let's the basis of quicksort. So if we want to make a definition for a quicksort, what can we say? For example, we have been given an array with n elements, and the elements are integers. So first we will check if the array contains one element, right? That means if we check the array contains one element, that means we don't need to make a sort, because it's only have the array only has a single element. So why we need to make a sort? It is already sorted. So if it contains more than one element, that time we need to make a sort. That means we need to sort the elements. So in that case, what we can do? In that case, we will choose an element as a pivot or pivot, because pivot actually handles the quicksort. And we will learn what is pivot and how can we choose the appropriate pivot. We will learn later. So partition elements into two sub-arrays. That means after picking the pivot, we will make a partition into two sub-arrays. And after the partition, we will see the elements that are less than or equal to the pivot. That means the left side elements. Before the pivot elements, all the elements are less than or equal to this pivot element. And the elements that are next to the pivot index or pivot values, that must be greater than the pivot elements. Then we'll perform quicksort on two sub-arrays, then return the result. So this is actually the basis for a quicksort algorithm. So we can say that quicksort in simple is a sorting algorithm, and it sorts the entire list of items by choosing a pivot element and then arranging the rest of the elements around the pivot such that all the elements less than the pivot is in the left side of the pivot, and the elements greater than or equal to the pivot move to the right of this pivot. Now we'll see an example how actually quicksort working. That means how quicksort works. For example, we have been given an array with n integers value. So here we have 9 elements, right? That means n equal to 9. And the elements are 40, 20, 10, 80, 60, 50, 7, 30, and hundreds, right? So we will perform a quicksort on these elements, right? So what was our first step? The first step is to check whether the array contains single element or more than single element. So in case we see that we have more than one element, that means the array contains a lot of elements, right? So in order to do that, first we will pick and pivot element. So you can check or we can choose any pivot elements. And what is the best way to choose the pivot element? We will learn later, right? Because the performance actually depends on choosing the appropriate pivot element. So we will learn this later. How can we appropriately choose or pick a pivot element? But in our example, or in this example, we'll use the first element as our pivot element. So for example, 14, 40 is the first element of this array. So we will select 40 as our pivot element. Now, second step is to make a partition, right? So given a pivot, we will partition the elements of this array in such a way that the result consists. That means the first sub array, the elements of the first sub array must be, that means the left side. The elements of the left side of the pivot element must be smaller than or equal to the pivot element, and the elements that are right side of this pivot element must be greater than pivot element, right? And after the performance, and after performing the sort partition, after performing the quick sort, we'll see the sub arrays are sorted in the original data array. Now let's see. So in that case, we'll perform two traverse, one from left to right, another from right to left, right? So how we'll perform this traverse? Based on the idea like that. So we will traverse, we'll check each item with the pivot element, whether it's smaller than the pivot element. So until it's smaller, we will traverse. That means we will forward to the next. That means we will forward left to right until we find the smaller elements. So, sorry, the bigger elements. When we get the bigger elements than the pivot elements, we will stop our traversing. Then we'll start from right to the left. And in case of right to the left, we'll check whether the element is, whether the searching element is smaller than pivot index. So whenever we see the element is smaller than pivot, we'll stop. Then we'll perform our swapping. And before swapping, we'll check whether the left index must be smaller than the right index, right? So if the condition satisfied, then we'll perform a swapping. And we'll continue this process until we find the appropriate position for the pivot element or pivot values, right? That means until 40 gets its own or its exact position, we'll perform these operations. Then we will perform our partition. Then after partitioning, we will see that we have two arrays, two sub arrays, right? Sub arrays 1, sub arrays 2. And we'll check whether the elements left side of the 40 must be smaller than or equal to the 40, and the elements of that are right side of the pivot element must be greater than the pivot element. Let's see. So we are checking the condition whether the, so until we'll check the smaller index must be the, that means the left side index must be smaller than the right side index. So until we find the greater value than the pivot value, we will traverse next, right? We'll forward. So you see, from the first index, we are checking this 20 still smaller than 40, so we can move forward. 10 is again smaller than 40, so we can traverse. 80, right now you see 80 is not smaller than the pivot element. So what I said, we said that until we find the bigger element, we'll move forward. So since we find the bigger element, so we'll stop here. So now our current index is 3. That means the two big index or left index is 3. Now we'll traverse from right to left, because we said that we will traverse, we will make it two traverse, one from left to right, another from right to left, right? So what we know about right in case of right traverse, we know that we will traverse from right to left until you find a smaller element. So 100, okay, compared with 40, 100 is still bigger than 40, so we can traverse. Sorry, we can traverse. Now 30 is now smaller than 40. Now it stops. right? It gets stopped because 30 is smaller than pivot elements. Now, since we get two stopping positions, now we can say that we will perform our swapping. So before swapping, what I said, we need to check whether the bigger index, whether the left side index must be smaller than right side index. So we say that the left side index is 3 and the right side index is 7. So condition is 3. So now we can swap our elements. That means 30 would be replaced with 80, right? Now we'll check, we'll repeat our operations until the left side index must be smaller than the right side index. So this condition is true. So go back to the step on. So again step on, right? Again, now our left side index. Now again we will start left traversing, right? The traverse from left to right. Then we will, after stopping, then we will start again right to left. So let's take the first condition. Okay, still now it's the left index is smaller than right index, so we can traverse, and we will also say that this elements is not greater than the 40. So 30 is smaller than 40, so we can traverse next. But whenever we reach to the next index, that means the index 4, we see that we got the element 60, right? The fourth index contains the element 60. The 60 is greater than 40. Now we will stop. Now our next move, right to the left. So we'll check 80. 80 is still bigger than 40. Now we traverse to the left, right to left. We move backward, right? So we'll check 7. Now 7 is smaller than 40. We'll stop here and check, and for the next iteration, that means the next step, we'll go to next step. And before doing that, we will check again the same way whether the smaller index, that means the left side index, is smaller than the right side index. Okay, this condition satisfied. Now we'll perform our swapping. That means 7 will be replaced with 60. Then we'll check again. The index must be, the smaller index must be the bigger index. That means the left side index must be smaller than the right side index. So until it's satisfied, we will continue this. That means we will repeat our operations, right? So same way we do that. Again, we are performing the same operation. For the next iteration, we see that 50 is greater than 40, so it stops and it gets the current index is 5. And for the right side traversing, we see that 60. So we'll move backward and we'll see 50. 50 still greater than the 40. Then we'll make another traverse. Then we'll see the 7. Now 7 is smaller than 40. Right? So we'll perform a swapping. But in that case, we cannot perform the swapping because one of the condition is false. You see, right now the rightmost index is 4 and the leftmost index is 5. So this condition is false. So we cannot perform a swapping. That means we exit the loop. And we will also check whether we need to check again from the first condition. We are seeing that the condition again false because the leftmost index is bigger than the rightmost index. So we exit our loop, right? We exit our looping condition. Now we will perform our swapping, that is main swapping. Now we can say that, okay, we get the exact position for 40, right? So the exact position is 4. So what the contents contained in the index 4? So we see that in index 4, the array contains 7. So 7 will be replaced with the pivot value 40, right? So after replacing that, we see that 40 gets its exact position. That means in that case, pivot index is 4, right? and we'll check whether the elements left side of the pivot value are smaller than or equal to the 40, or the elements that are right side of the pivot values are greater than the 40. Let's see. So after making the partition or partition result, we see that we have successfully partitioned into two sub-arrays. The left sub-array contains 7, 20, 10, and 30 that are smaller than 40, and the right array contains, then the right sub-array contains 50, 60, 80, and 100 that are smaller than, sorry, that are bigger than the 40. So condition satisfied. That we say that the quicksort is working perfectly. So now our next step is to perform quicksort using recursion. That means we'll perform the same things on the left side array and the right side array. So after doing that, we'll see that, right? So in order to do that, we can design, or there we have a pseudocode like this. So we have a two, we know that there are two types, we need to perform two operations. First, we need to make a partition. Then after partitioning, we will have two sub-arrays. Then on these two sub-arrays, we need to perform quicksort. That means we need to perform two quicksort on two sub-arrays until we find the sub-arrays are sorted, and the sub-arrays contains the single values, right? Until the sub-arrays contains single element, we'll repeat these operations, right? So we can write our pseudocode. So this is the pseudocode for quicksort. So I hope you understood what is the basis or how quicksort works. Now we will learn, or we will perform an analysis. That means we will perform, or we will calculate the time complexity and space complexity for quicksort. So we can assume that the keys are random and the elements are uniformly distributed. So what will be the time complexity in that case, right? So there are two cases we will consider. One is the best case, another one is worst case. The quicksort best case occurs when the partitions are evenly balanced as possible. Their sizes either are equal or within one of each other. The former case occurs if the subarray has an odd number of elements and the pivot is right in the middle after partitioning, and each partition has n-1/2 elements, right? The later case occurs if the subarray has an even number n of the elements and one partition has n/2 elements with the other having n/2 minus 1. In either of these cases, each partition has at most half elements, at most n/2 elements or n/2 elements. And the tree of subproblem size looks a lot like a tree of subproblem sizes for merge sort, with the partitioning times looking like the merging times, right? So what do we learn from there? So in the best case scenarios, we always see that, or we always assume that the partition makes a partition on the array elements into two sub-arrays, and the contents or the elements of each sub-arrays almost similar, right? That means if we have the elements, if we have an array with elements, for example, 5, then after partition, and the partition makes the position third, that means the left sub-array contains 2 elements and the right sub-array contains 2 elements. That means we can say that we choose the pivot elements in the middle element, right? So in that case, what happens? So in that case, we can design our quicksort. That means, so quicksort with taking the number of n elements. So we know that we need to perform three operations. First one is, sorry, actually two operations, but three times. So first we need to perform a partition. So after partitioning, we'll perform two quicksort, right? On quicksort for the left side subarray or left subarray, and other quicksort will perform for the right subarray, right? That means the data are split half and half. So, so the amount of work, that means amount of work done by quicksort, that means how many words we need to hold, right? So amount of work, so total how much work we need to do for this quicksort. So we can calculate the amount, like, so total amount should be the amount of work done by the partition part with total elements plus the amount of work done by the quicksort using half of the elements, plus, that means half of the elements means the elements of the leftmost arrays, and the work done by quicksort using the elements of rightmost arrays. So if we want to define in a formal language or formal way, we can say that T of n, that means time of, that means total time should be partition n, that means for the partition plus T of half n, right? And plus T of half n, because we are using half of the elements for the left array and half of the elements of the right array. So we can say that partition plus 2 into T of n over 2, that means T over half of n. So using the recurrence relation, we can solve this equation, and we got that the total time is n log n. And using the binary tree or decision tree, we can also see that we know that each step is taking the half of the elements, right? That means every time we choose the pivot element as the middle element. That's what we make a partition half and half. That's what after every step we see that the elements are splitting by half. So until the elements, we got the position, we got the array, sub-array contains a single element, we'll make a split, right? We make a partitions. So for example, we say that after k steps, we got the value 1. That means the array contains single element. That means our splitting is stopped. So we can calculate this. So for example, after the k steps, so n over 2 to the power k should be 1. So n should be 2 to the power k. Then after applying the log function for both sides of this equation, we see that k equal to log n, right? So its process time is log n. Since it takes total number of n elements, that's what the time complexity for the best case scenario would be order of log n, right? So this is the best case scenarios. Now we can consider another case, worst case. So what is the worst case? So before calculating the worst case complexity, we'll see what happens during the worst case, right? For example, we have given the same arrays and assume that the array is already in sorted. Actually, worst case happens when the array already sorted. Array is already sorted. Actually, whenever we get an array and the array is sorted, and worst case actually happens that time. For example, the same data, but the array already sorted. So by the definition, we'll choose or we'll pick again the first element as our pivot element, and we same way we'll follow the same way. That means we'll perform a traverse from first traverse from left to right, and the second traverse right to left, and we'll check the condition, the same algorithm condition, right? So what happens? Let's see. So the first in will check the left index must be smaller than the right index. So until get the smaller element, right, we will traverse. So 4 is small and still bigger than 2. 10 still bigger than 2. 12 still bigger than 2. 13 still bigger than 2. 50 still bigger than 2. 57, 63, 100. And we almost reach to the rightmost element. So there is no other element. So we cannot traverse. So we can stop here. Right? Now for the right traverse. So he will search until he finds the smaller element than the pivot element. So 63 still bigger than 2. 57 bigger than 2. 50, 30, 12, 10, 4, 2. Right? That means rightmost index reached to the leftmost index. That means it crossed. Right? So still, whenever he finds his own position, now he can perform the swapping. We say that, but in that case, it will not perform because the leftmost index is smaller than the rightmost index. So it will not perform this type of swapping. So it will exit. Then it will check for the next iteration. For whether it will go for the step 1. No, it will not go for the step 1 because you see the left index is smaller than, sorry, left in the rightmost index is bigger than the leftmost index, sorry, smaller than the leftmost index. So it will perform the final form. That means it exits the loop. Now it will, we know that it will replace with the rightmost index value with the pivot index values. So after checking this, he is checking that he is replacing by himself or herself, right? So we know that the rightmost index value is 2. Sorry, rightmost index element is 2 and the pivot elements also 2. So after replacing that, that means he is replaced with himself. That means 2 gets the position where he already was, right? 2 now gets. So we know that after getting the 5th step, so whenever we reach to the 5th step, so after executing the 5th step, we know that the pivot achieves his or her best or accurate position or exact position. But we can see that after replacing that, we see that 2 gets his exact position, but he was already was in that position, right? So after making a partition, what we see? So after making the partition, we see that the instead of regardless of this the first element, the rest of the elements are the right side, and in the leftmost side there is no element. So the rightmost side, these are the right subarray, right? So in that case, so we know that we will perform again after partitioning. We will perform our quicksort on the 2 subarrays. So we don't have any left subarray, only we have the right subarray. So similarly, in that case, we will choose 4 as an pivot elements, and after executing or after iterating all these steps, we will see that 4 is getting his own position, and he will check that 4 is already in his previous position. So one by one step, you will see that. So that means when quicksort always has the most unbalanced partitions possible, then the original call takes time n. That means takes the cn time. C means the constant times for some constant c, and the recursive call on n minus 1 elements. That means after every partition, it takes number of n minus 1 elements for doing his operations, and it takes the time for that. So if it takes the elements number of n minus 1, then it will take the time n minus 1. And after this iteration, the element should be n minus 2, and it will also take the time n minus 2. That means it's taking the constant time. So after this iteration, that means how can we design that time or quicksort? That means how actually quicksort behaves. So in that case, Quicksort makes a partition with n elements. Then after the partition, he sees that the left, the right, rightmost, the right sub-array contains n minus 1 elements, right? You see, the right elements contains n minus 1 elements. And the left array contains no elements, right? So if we want to define as a formal language and a formal definition, so the total work done by the quicksort should be the amount of work done by partition plus amount of work done by the quicksort on rightmost array plus 0. 0 means we don't have any left side array that time, right? So total time should be partition plus time of n minus 1. We can easily say that. And using the decision tree, we see that after every step, it's taking n minus 1 elements, right? First, it takes n. In the first step, he takes a number of n elements. After the first step, that in first iteration, he takes n minus 1 step, n minus 1 elements. After then, he takes n minus 2. After then, n minus 3. So until he gets the single element, he is taking n minus 1 element. So the time complexity should be like n plus n minus 1 plus n minus 2. So if we calculate this, we can get this. It is the n square. So in the worst case scenario, the time complexity should be order of n square. And we can also solve this using recurrence relation, right? So the quicksort analysis, for if we perform an analysis for the worst case, we will see that using the big notation, the time complexity for quicksort, the time complexity of quicksort for worst case is order of n square, right? Now, what is the average case runtime? So we'll learn later. Now, space complexity. What is the space complexity? Right? Quicksort with in-place and unstable partitioning uses only constant additional space before making any recursive call, right? Quicksort must store a constant amount of information for each nested recursive call, since the best case makes at most order of log n nested recursive call. We already have seen that. It uses order of log n space. However, in worst case, Quicksort could make order of n nested recursive call, right? And it also needs order of n auxiliary space. So from a bit complexity viewpoint, variables such lower or right do not use constant space. It takes order of log n bits to index into a list of n items, because there are such variables in every stack frame. Quicksort requires order of log n square bits of space. So this space requirement is not too terrible, though, since if the list contained distinct elements, it would need at least order of n log n bits of space. So we can say that for quicksort, the space complexity for the best case, it should be order of n, and for for the worst case, it should be order of n, because the algorithm because when the algorithm encounters its worst case where getting a sorted list, and we need to make an n recursive call, right? And in case of best case or the average case, the space complexity should be order of n, because we know that the quicksort always is the in-place version, right? So we can summarize the space complexity for worst case order of n, and for average case and best case order of log n, right? Now we'll perform or prove That means we'll prove the correctness of quicksort. That means we'll try to prove the quicksort is working perfectly. So there are several ways to prove correctness of an algorithm using proof by induction, using loop invariants, etc. So in our example, we'll apply proof by induction. So before applying this, we need to know the basis of proof by induction. So what is proof by induction? Proof by induction means we are going to prove some property like P, right? We want to prove P. So in that case, we'll perform three steps. One is basis step, second one is hypothesis step, and the third one is inductive step. Basis step means we'll perform our assumption, or we'll perform for the one. That means the sum statements regarding P of 1. That means for the value 1, we'll perform our base test. Then we'll see that it performs okay and is working correctly. Then we make an hypothesis for the hypothesis step, and we'll assume that we'll consider, or we'll assume that it will also perform quickly. That means it may perform quickly for n. And the inductive step, we'll say that if P of n is correct, then P of n plus 1 must be correct, right? And we'll prove that P of n is working perfectly since P of n is true in our hypothesis step. So let's start to define. So our quicksort algorithm, right? So in our quicksort algorithm, what we do? First, we check whether the array contains a single element. That means how can we check that? That means if left index, that means left index must be smaller than right index. Left index means it starts with the left index means at least one value, and right index means whenever the right index you get the 2 or 3 or whatever. So if we check the left index is smaller than the right index, then we can perform. First, we will partition the array into 2 sub-arrays. Then we will perform 2 quicksort on these 2 sub-arrays, right? So this is our actual algorithm. Now we'll take our basis step. So in our basis step, we'll check n equal to 0. That means the array contains no elements. N means our number of elements. That means array contains how many elements, right? So n means 0. That means array has no element. So we can perform the quicksort. So in that case, the array should be, so A is our array, and the leftmost. So L means 1 and right means 0. That means right index is 0. That means, so the condition is false, right? Because L greater than R, and the algorithm returns correctly an empty array. So we don't need to perform quicksort. That means this condition is true. That means, sorry, this condition gets false. So we don't need to perform the partition or quicksort because we see that the array is empty. So what happens if the number of elements is 1? So that time we see quicksort. So quicksort, our array and L should be 1 and R should be 1. That means in that case, L equal to R, right? Still it is false. Right now, what we said in our algorithm before starting our algorithm, if the array contains more than one element, then we can perform our quicksort. But in that case, we see L equal to R means the array contains a single element. And if we see that if an array contains a single element, that means we don't need to perform any sorting strategy or sorting technique, and we will say that the array is already sorted because the array contains a single element. Now the inductive step. Inductive step means we'll consider or we'll assume for specific values. That means it must be greater than 1, right? So whatever we considering a value, that must be greater than 1. So in that case, for example, we are considering n equal to k values. So let's assume that the quicksort for the array starts with 1 and the rightmost index is k. That means k may have some values, 2, 3, 4, whatever. So returns and sorted arrays of size. So we are assuming that the quicksort works perfectly and returns a sorted array of the size k. That means this hypothesis extended to all. That means n smaller than or equal to k. That means k must be greater than n. Right? So this is our partition algorithm. Now we'll check whether, because we know that right now the number of elements are greater than 1. That means the array contains more than 1 elements. Now we can perform the partition. So based on the condition, you see, based on the condition, if r, so in that case r is k, right? So k is greater than l means 1, so more than 1 elements. Now we can perform our partition. So we see how it works. So in our inductive step, we will prove also. So because what do you know? What do you say that in our hypothesis step? In our hypothesis step, we assume that it works for k. So in our inductive step, we can easily say that we will prove that it will also works for k plus 1. And through our step, through our explanation, we'll see that it perfectly works for k plus 1 elements, right? That means in the inductive step, we need to prove that. We need to prove step by step that the quicksort works perfectly and returns a sorted array for k plus 1 elements where k must be greater than 1, right? So let's think outbound. So we want to use our hypothesis for n smaller than or equal to k and observe the code that must be caused the two quicksort, right? Because we have more than 2 elements. So we have left subarrays and we have right subarrays. So after the partition, we know that we need to make a partition. So after partitioning, for example, our partition position or the pivot position is P, for example. P is our pivot position. So the left elements must be starts with 1 to just before element of the pivot element. So our pivot element is P. So the element should, in that case, L should be 1 and R should be P minus 1. And the right array, it will be the leftmost index should be just after the P index or the pivot index. So it should be P plus 1 and the right index. We know that because we have we have R equal to K plus 1. So intuitively, if these sorts are on arrays with size n smaller than or equal to k, so we can use our hypothesis to say that these are sorted correctly. Now it's time to formal proof. So we will formally prove this. Now our inductive step. So in our inductive step, we'll try to prove that the quicksort works perfectly for k plus 1 elements. Now, in that case, we have L equal to R, right? Because we start from the index, first index, and R equal to K plus 1. So the condition is satisfied, right? The partition. Before doing the partition, the condition is to satisfy. That means, in our case, K R equal to K plus 1, and we know that K greater than 1, it might be 2, 3, 4, 5, whatever. So if it is greater than 1, that means the condition is true. So it will perform the partition. That means it will perform this state partition. And after the partition, it returns the partition position. We know that. That means it returns the exact position for the pivot values. Right? So in the partition, The I variable states that L, which is 1, it is incremented by 1 whenever A of R, that means the rightmost element, is bigger than the leftmost element, right? Bigger than the AJ means our rightmost index, where J must be greater than or equal to J, greater than or equal to 1, or smaller than or equal to J, right? So similarly, I also same. So I should be greater than or smaller than 1, and smaller, and must be smaller than or equal to K. So which is then assigned to variable P. So again, so after the partition, so after this partition, after this statement execution, we will see that the leftmost array should contains, that the leftmost array is 1 to P minus 1, because P is our pivot position, right? The pivot index. So it must be smaller than or equal to pivot element. And the rightmost array, it should start from the, for example, P to K plus 1. Right? It should be actually P plus 1. P plus 1 to K plus 1 must be smaller, greater than pivot values. Right? So after the inductive step, we will see. Right? So based on the definition, we will see that the elements that are left side of the pivot value must be smaller than or equal to pivot element, and the elements that are right side of this pivot element must be greater than pivot element, right? So after the partition for the K plus 1 elements, it will prove that, and it will, and it not actually, it will prove that, it will actually show us the elements that are the left side of the pivot element must be smaller than of the pivot element or equal to pivot element, and the elements that are right side of the pivot element that must be greater than the pivot element, right? So then we can call our quicksort. So after partitioning, we need to perform quicksort, that means two quicksort for the element from 1 to P minus 1, and another quicksort for the right elements, right side elements, right? So it starts from P plus 1 to K plus 1, right? So in our inductive step, so we'll prove that quicksort A, now our array is A and starts from 1 to K plus 1, correctly returns a sorted array with size n equal to K plus 1, where K must be greater than 1. Then we can call, so after, then we can call two quicksort, right? A equal to 1, P minus 1, 1 for P minus 1, and another quicksort P plus 1 to K plus 1, right? So after that, we'll see that the quicksort for the using the first arrays, the first sub arrays index, and it is returning, and this quicksort for these elements 1 to P minus 1 correctly returns the sorted array, right? And for the elements that are right side of the pivot elements, so after this, after executing this quicksort, we'll see that it also returns an array with the elements that are rightmost side of the pivot elements, also returning and sorted arrays correctly, right? If the elements start from 1 to P minus 1, then just before the pivot index, that means it must be, we know that must be smaller than the pivot index, and the elements that are right, or that are next to pivot elements to until rightmost index, it must be greater than, right? So the quicksort, so if this condition satisfied, right, we will definitely say that the elements, right, the left side elements, the sub array, that means sub array 1, A1 returns a sorted array. Similarly, the rightmost array, the rightmost sub array it also returns and sorted array, right, correctly. So that means the total array after merging that number, after combining the, after the conquer, or sorry, after the combined step, we'll see our total array, that means 1 to k plus 1, right? 1 to k plus 1 are sorted correctly. So our algorithms correctly works. Now some challenges. I told you, whenever we are trying to picking the better pivot element, we say that because we know that the performance of the quicksort actually depends on selection of better pivot, right? We pick the first element of the sub-array to use as a pivot, right, in our example. And we say that if the array is already sorted, this results gets the order of n square behavior, right? Because then that time it achieves the worst case scenario, and there is no better if we pick the last element. So no matter if we pick the last element or first element as our pivot, we cannot change the behavior because we know that the arrays are sorted. So in that case, what we can do? How can we neglect, or we can consider this? We are not, if we want to, or if we don't want to get the worst case scenario, worst case performance, what we can do? How can we remove from this situation? So we have an optimal options. We can perform, or we could do an optimal quick sort that can assist best case scenario. So in that case, the main concern is to how we efficiently select the or pick the pivot values. So if we can select the pivot value exactly the correct element, for example, if we can select the pivot value, the middle value, if we select the middle value as our pivot value, that means the after picking the pivot value that exactly cuts the array in half. That means we select the middle value. This value actually called a median. And the median value, half of the values in the array are larger of the median value, that in the pivot value, and the half of are the smaller. So in that case, no matter the array is sorted or not, if we can select the middle value, that means the median, if we apply our median concept. So what do you mean by median? Median means if from an array, for example, we have elements 1, 2, 3, 4, 5. These are sorted, right? And if we select the 3 means just middle element. This is called median. So if we can select from the sorted array and the middle element as our pivot, that means the array, the pivot elements, or we can say that the partition or the divide step divides or makes a partition of the arrays half and half. And we know that if we reached a condition where the array after the partition, if the two sub arrays gets half and half data, that means we can achieve the best case performance, and we will have the time complexity, that time order of log n, so we can perform better, right? So if we can pick a better pivot, or we can perform a median concept, or we can apply the median, then we can get a better performances, right? So we can say that how can we improve the pivot selection? So we will pick the median value of the 3 elements from the array. It should be the first position, or for the last position, and the middle of this position, right? So we will check always the middle position as our pivot. So if we can successively pick the pivot middle element, that means the array gets half and half, and we will achieve a best case scenario. That means for no matter the array is sorted or not, right? So we can optimize this way. Another way, we can follow the randomized concept, right? So what is randomized concept? Randomized concept means, so that means in order to do this, we have a question like, how can we modify quicksort to get good average case behavior all the inputs, right? Instead of worst case scenarios. That means no matter the input types or no matter the inputs, how can we always perform good average? So in that case, we can apply the randomized, or we can apply the randomized concept. The answer is randomization. That means we can apply randomization technique on the quicksort. And there are two techniques how we can apply randomization. The technique one is randomly permute input prior to running quicksort, because it will produce the tree of possible execution. Most of them finish fast. And the second one is we'll choose the partition randomly at each iteration instead of choosing element in the highest array position, right? That means we'll choose randomly. After every iteration, we'll choose the, that means, for example, after the partitioning, that means after this step, whenever we need to perform or we need to repeat the action, that means, let's say second iteration, we'll choose another random value as a pivot value, not like the selecting the first position value or the last position values, right? So if we perform these operations, if we perform like this, then we can optimize our performances. Then we can always get the good average case instead of getting the worst case. And if we want to make a randomized quicksort where we need to change, we'll have the same code, just we need a little bit trick change. For example, in that case, first we'll perform a random selection. That means we'll randomly select a pivot value, not like the selection of first element or the last element, right? In that case, we will randomly select from the left index to right index. So any of the values from the array we can check. It will randomly select. And after selecting randomly, we will change with the elements, with the rightmost elements or leftmost elements. You can change either with A of L or A of R. If you want to treat it this pivot element as the last element, then you can change with this element R, or you can check with left. If you perform the whatever we follow the example, then we can check here A of L, and the rest of these things are same. So after every iteration, we'll perform a randomization. That means we will randomly select the pivot elements. So in that case, we can get rid of the worst case scenarios, right? So these are the improvisation or improvement of quicksort. So again, we are saying that the improvisation, the quicksort, that means we can do this shuffling the list before sorting, median of 3 partitioning, and also parallel quicksort. So what is the shuffling? The list before sorting. Shuffling the items of the non-sorted list can give a better guarantee that the list is not nearly or already sorted, which make the worst case performances of the quicksort. Shuffling the item gives better randomness in elements position, thereby helping the quicksort to perform better, right? And another thing is median of the 3 partitioning. So a second easy way to improve the performance of quicksort is to use the median of the small sample of items taken from the array as the partitioning item, that means as the pivot item, right? Or the pivot values. Doing so will give a slightly better partition, but at the cost of computing the median. It turns out the most of the available improvement comes from the choosing a sample of size 3, right? And another technique is parallel quicksort. It is possible to optimize quicksort by running the recursive calls in parallel. We end up in calling the quicksort on both the left and the right partitions of the data set. The most vital thing is that neither of these two partitions has to be compared to one another after the individual division of elements. We can run both recursive calls on both partitions in parallel. When we run two quicksort calls in parallel, we are effectively spawning two different tasks in order to run them at the same time. We sort each partition of the array independently using same amount of space, but only half of the time we did before, right? This is often referred to as parallel quicksort. So now we see some quick review on quicksort. And based on our example or the basis or the analysis, we see that the running time depends on how well partition divides the array, right? So the running time actually depends on how we efficiently make a partition. In the example above, it does reasonably well, right? And if the array is partitioned nicely in two halves, right? That means the left sub-arrays have the half elements of the arrays, main arrays, and the right side have the almost have the same like the half of these elements. That means we can get the best case performances, right? So in that case, the time complexity is order of n log n. But in case of worst case, partition always returns order of n square, right? Because we know that in the worst case scenario, the array is always sorted. So from this definition or from this, what we can say? So we can say that all good splits give us order of n log n. That means if we efficiently split the or efficiently make a partition of the data, then we can get order of n log n. That means we can achieve best case scenario. And if we have the all bad splits, then it will give us worst case scenario. That means order of n square. So what about a combination of good and bad splits, please? And note that a good split is not necessarily a perfect balance on. That means it doesn't mean that if we have half and half, that means left sub-arrays has the half of the elements of the main array, and the right side also has the half of these elements. So it doesn't mean that it is on the best for this or it is the perfect balance. So any selection that any split that puts a constant fraction of the elements is on site is also good. For example, based on the trial and error basis, we see that some splits are also perform good, gets the best average case or get the sometimes it also perform the average case. That means it also achieves the we know that in our average case it achieves order of n log n, right? So some splits also perform good, not only half and half. For example, 9/10 with 1/10, it also get the order of n. Half and half to half, 1/3 or 2/3. That means 60/40 or 35/65, or sometimes we can say 20/80 or 90. So these also are good splits. So if we can perform this type of splits, then the quicksort may achieve the good average. And we can achieve and we can get the order of n log n instead of n square. Right? So some questions now. So what is the average case runtime complexity for quicksort? So we know that. What is the time complexity for best case? What is the time complexity for worst case? So now if we consider the average case, so what will be this? So previously, in the previous slide, we see that if we can make a good split, right, like 30, 35, 65 or 25, 75 or 20, 80 or 90, 10. So if we make a like good split, at least on site, then we can perform and we can achieve a good average case, right? So for example, how can we get the best average case scenario? So let's imagine that we don't always get evenly balanced partitions, but we have always get a worst like 3 to 1. That is, imagine that each time we partition, one side gets 75% elements and the other side gets 25% elements. That times we can get a good average, right? Then the tree of subproblem sizes and partition times would looks like this. You see, like this. For example, after making a partitions, for example, our left side gets the 25% of the elements. So, for example, we have 10 elements. So, in the left side, we will get 3 elements or 2 elements, and the right side we will get the 75% of this. So how can we calculate this? So every time, so after each time, that means we are saying that our left side, our left sub array contains the 25% elements, and the right sub array, it gets the 75% elements, right? So after applying the recurrent solutions, we will see that we can get the performance, like we can achieve the time n log n, right? So this is the calculation. How can we get the average case running time complexity, right? The next question is Quicksort a stable algorithm? No, Quicksort is not a stable algorithm because the swapping of elements is done according to the pivot's position without considering their original position. A sorting algorithm is said to be stable if it maintains the relative order of records in the case of equality of keys. Now the next question. Is Quicksort an in-place algorithm? Yes. Quicksort is an in-place algorithm, which means the number of all sorted within the original array itself, right? Now, what is the randomized quicksort and why it is used? We already discussed what is the randomized quicksort, but we are going to repeat again, right? Sometimes it happens that by choosing the rightmost element at all times might result in the worst case scenario. In such cases, choosing a random element as your pivot at each step will reduce the probability of triggering the worst case behavior. We will be more likely choosing pivots closer to the center of the array. And when this happens, the recursion branches more evenly, and thus the algorithm terminates a lot faster. And the running time complexity is expected to be order of n log n, as the selected random pivots are supposed to avoid the worst case behavior. Now, why quicksort is better than merge sort? Quicksort is an in-place sorting algorithm, whereas merge sort uses extra spaces, right? In-place sorting means no additional storage space is required to perform sorting except recursion stack, while merge sort requires a new temporary array to merge the sorted arrays, thereby making quicksort the better option. Worst case scenarios. The worst case runtime of quicksort is order of n square, can be avoided by using randomized quicksort, as explained in the previous point, right? Obtaining average case behavior by choosing random pivot element improves the performances and becomes as efficient as merge sort. Case friendly. Quicksort is also a case friendly sorting algorithm as it has a good locality of reference when used for arrays. Now, which is faster, quicksort or merge sort? I will say quicksort is faster than the merge sort, right? And where it is used? The next question is, where is quicksort used? Quicksort is basically used to sort any list in fast and efficient manner. Since the algorithm is in place, quicksort is used when we have restrictions in space availability too, right? So that's all for today. If you still have any question regarding this quicksort, please email me. Thank you.